I'd just like to announce that that university gate will again close at 7 o'clock. So whoever's parked their cars on that side can get it this side and then exit through the other exit, through the Bhau Patil Road exit, the Aun side. I'd also like to announce that there are washrooms to the left and drinking water, filtered drinking water, again on the left side of this building. Okay, so good evening everyone, and thank you so much for coming here today. This is the third of our series of great talks, and we are happy to host this one with Ayuka. How many are library members? If you could just put up your hands. Great, thanks so much for coming. I know it's a slightly out of the way place, but we're so happy that this is a huge auditorium with all the stuff, and we've had Dr. Jane from morning, and she's already visited one school in Pune, and she's spoken to a few journalists, and now we'll be soon starting this program. If you have any questions, we will pass the mics around after she's finished her talk. And feel free, all the school kids, all the kids here, feel free to ask her because that's what she enjoys doing. I mean, her major role is of a public engagement person, and she believes in popularizing science. So, many of you know the British Council in Pune as just a library. But we are very excited to let you know that we have just moved to a new place where we function not only as a library but also as a public cultural convening center. How many of y'all have visited us either for the drums, okay, Café Scientifique, which is again something that we do with Ayuka. So we were very happy that Dr. Shomak was the first one to inaugurate it when we opened on the 3rd of September. And we tend to do programs in partnership with many other organizations. So we do Café Scientifique with Ayuka. We do a lot of art programs with Art Sphere. So last week we had the workshop on how to improve yourself to dance therapy. Did anyone attend that? No? Okay. This is a completely different set of audience. So what I wanted you is to visit us at the new place. So whoever is not a member, if you could come in, we do group visits on Wednesdays and Fridays. And we would be very happy to show around all the school children or even other groups like college students. We also are very happy to let you know that we have a Twitter handle which is called as In British, which you can keep an eye out for the different things that are happening, not only in Pune but also around India. So right now we have this huge project of the moon, which is in Udaipur today. And we have just also completed, as part of the wider network thing, we have just finished our Education UK exhibition. Did anyone attend that? Education UK exhibition? Okay, that's for people who are interested in studying in UK. So I now hand over the mic to Samir, and he will take you through the rest of the program.
Thanks, Kajri, for welcoming everybody. But I, of course, have to welcome you all on behalf of IUCA to this great talk that we are, all looking forward to today evening. IUCA is the Inter-University Center for Astronomy and Astrophysics, and with our long tradition for scientific outreach, we've been holding regular public talks related to astronomy, science, and other crossover fields in general. So we have this very special program coming up at the end of this month on 28th February, which is the National Science Day. So I am just doing a plug here, an advertisement for the program, for which all of you are welcome. It's a weekday, we know, but I mean, over the last few years, we've seen that even on weekdays, we get around 8 to 10,000 people here at IUCA. So please be amongst those people who visit IUCA, because there'll be a lot of infotainment happening, a lot of information, entertainment, and you'll get to know the details about your favorite astronomy objects, favorite astronomy projects, everything that IUCA is involved in. So with that, I'll quickly move on to today's program. So in collaboration with the British Council, we are hosting the great talks, especially the ones given by astronomers from UK. And we are very happy to have Professor Dr. Jane Gupta here. But to introduce her, I will welcome on stage Professor Somak Raichaudhary, our director, who has also had his education in the UK, so he'll be able to put it a nice perspective to that. Thanks, Joe.
Good evening. I'm so happy to see all of you here. I won't take very long because I'm not the speaker today. My name is Somak Raichaudhary, and I was quite surprised when Kajri said that this is IUCA is quite out of the way. We tend to think this is the center of the universe. Don't you think so? Actually, if you are interested in astronomy or anything to do with science, and you haven't been to IUCA before, think of this as out of the way. Please keep an eye on what's happening here, because a lot of stuff happens here. As Samir said, actually on the National Science Day at the end of the month, you'll also find that there will be, if the sky is clear, various activities in the evening as well, and during the day. And one of the highlights of that program is in the afternoon, there'll be Professor Jayant Narlikar answering questions from the audience, and also there'll be lots of stuff going on all over the place. Anyway, coming back to our work with the British Council, the Café Scientifique is going well, and I'm really happy that we can be hosts to some of the great talks. We of course have a regular public talks program in this auditorium, and please keep an eye on them. They're also webcast. If you can't come, you can actually watch them on our YouTube channel. I'm very, very happy today to welcome Dr. Jane Gupta from the University of Portsmouth, which actually has a very, very important center for cosmology and gravitation, where a lot of the extragalactic astronomical research is done. Jen grew up in England, born of Indian parents, of course, but in England, and then she did her undergraduate and graduate work at the University of Manchester, which of course has the Jodrell Bank radio telescope, as you know, and she's worked on AGN, supermassive black holes in the middle of galaxies, and evolution of galaxies and things like that. And since then, she joined University of Portsmouth. She'll tell you a little bit about her department and her role there. And recently, the Royal Astronomical Society named her among 21 women in the 21st century to look out for, and certainly we'll look out for her. And of course, the BBC's flagship science program, Tomorrow's World, now is a broadcast on YouTube and the internet, for anybody in the world to see, and Jen is one of their live presenters. So I hope that her role in broadcasting and telecasting of astronomy is going to increase. I'm very happy to present you to Jen, Jen to come on and give a talk, and I hope there will be a good exchange of questions and answers afterwards. Jen.
May I request all of you to turn your mobile devices to silent? Thank you.
Thank you. Good evening, everybody. It's an absolute pleasure to be here. Thank you for those Introductions. As was said in the introduction, my name is Dr. Jane Gupta. I'm an astrophysicist and a science communicator from the UK. And so my role day to day is that I work for this department that's been mentioned, the Institute of Cosmology and Gravitation at the University of Portsmouth, where my job is as the public engagement and outreach manager for this department. And so what this means is that my job is to do things like this. My job is to give public talks, is to go to visit schools and talk to school children about astronomy and space, and to encourage the rest of my department to do the same. If you're wondering where Portsmouth is, if you've never heard of Portsmouth before, it's on the south coast of England, so we're on the seafront. This map shows you Portsmouth down here, and this is London up there, so we're about an hour or an hour and a half travel southwest of London. As was mentioned, I did my PhD in astronomy and astrophysics at the University of Manchester, and for this I used telescopes around the world to study these galaxies that we call active galaxies. And I'm not going to tell you much about that now because I'm going to come on to that later. Here's a photograph of me standing inside a radio telescope, the Very Large Array, in New Mexico. But actually one of the main telescopes, radio telescopes, that I used as part of my PhD studies was the GMRT, the Giant Meter Wave Radio Telescope, here in India, operated by the NCRA on the other side of the road. And I would describe myself more generally as a science communicator, a science comedian. I sometimes do short comedy sets about astronomy. You can find some of those on YouTube. And a science presenter. So I have my own podcast. This logo here on the right is from my podcast Seldom Serious, which is all about me and my friends talking about astronomy and having the kind of conversations that we would have over dinner or over a drink, but we're recording them instead over Skype. And then, as was mentioned in the introduction, I've also started doing much more presenting for organisations like the BBC. And so last year I was doing these Tomorrow's World live shows with my co-presenter Hannah. And those are on Facebook and YouTube if you want to watch those. And so I work for this department called the Institute of Cosmology and Gravitation. My laptop was trying to connect to the internet, sorry about that. I work for this department called the Institute of Cosmology and Gravitation at the University of Portsmouth. We're a research institute. We're a bit of a hidden gem, so not many people know about the ICG, even in the UK, but we're actually one of the best departments in the world for the research that we do, this astrophysics and cosmology. And so I want to talk to you a little bit about the research that we do there, but before I do that, I just wanted to make sure that everyone here knew about the different terms that I'm going to use, because I'll talk about astronomy, I'll talk about astrophysics, and I'll talk about cosmology. But what do all those three terms mean? And so I like to think of astronomy, and these are my definitions. Other members of the audience might not agree with me. But I like to think of astronomy as using telescopes to observe things in space, to observe planets, to observe stars, to observe galaxies, and to make measurements of them. So we look at planets like Saturn, we look at galaxies like this one here on the right, and we measure how bright they are. We measure what color they are. We measure how far away they are. We use our telescopes to do this. I would then describe astrophysics as using our knowledge of physics to interpret those observations of these objects in space. And so we use all of those laws of physics that we know about here on the ground, the laws of gravity, of forces, of magnets, and we use them to explain why the objects in space are the way they are. So one example of that is looking at the sun. This is actually a photograph of the sun taken a couple of days ago by a NASA spacecraft called the Solar Dynamics Observatory. And so you can actually go, if you put into Google the sun now, you can actually find photographs of the sun taken that day or the day before by a spacecraft, which I think is absolutely incredible. And so what we can do is we can look at the sun and we can say, well, the sun is this bright, the sun is this hot, but why is it like that? Why is it giving off this light and this energy? And what was realized was that the sun is powered by this process called nuclear fusion. Just turn off my... And so what's happening in the sun is that these atoms are smashing together to form new atoms, and that's giving off energy which we see as the light and the heat of the sun. And then the other term I'll use is cosmology, and this is a lot of what we do at Portsmouth. It's in the name of our institute. Cosmology I would describe as using observations and physics to understand the universe as a whole. So a cosmologist might not care about what an individual galaxy looks like, but they will care about where all the galaxies are and what that tells us about the history of the universe. And so that's what's shown here in this picture. This spider web-like structure shows us where the galaxies are that are near to us. So every point on here is another galaxy. And what we can do is build fake universes inside of computers and make them form structures, make these fake universes form galaxies, and see if our simulations match up with our observations. So the research that we do at the ICG, we really look at the big parts of the universe, extragalactic astrophysics and cosmology. And so I have colleagues who study galaxies, like this spiral galaxy here, looking at their shapes, looking at their colors, looking at the stars within those galaxies, what we call the stellar populations, what types of stars are in what parts of the galaxy, to understand how galaxies have formed and how they've changed with time. One of the projects we're involved with is this one called Galaxy Zoo. I don't know if any of you have heard of this, but Galaxy Zoo is a website, a citizen science project, where we put our photographs of galaxies online. Because there's millions of galaxies out there, and we want to know what every galaxy looks like. We want to know its shape. But there's too many of them for astronomers to look at. This project started when a PhD student called Kevin looked at 50,000 galaxies in a week, wrote down what they looked like, and said never again. And so, in the pub with his friend Chris Lintott, who's the presenter of The Sky at Night in the UK, they thought about how can we do this in a different way? How can we make it so no PhD student has to do what Kevin did again? And what they realized was that humans are really good at recognizing shapes, at recognizing patterns. Computers aren't very good at this. It's really hard to train a computer to tell us what something looks like. This is why facial recognition software is still in early stages of development. But humans are really good at recognizing patterns. So the pictures were put online at galaxyzoo.org, and members of the public were asked to classify galaxies. And Galaxy Zoo has resulted in over 40 science papers using those classifications from members of the public. So if any of you want to get involved with the research that we're doing in Portsmouth and our colleagues in Oxford and other institutions around the world are doing, then you can go to Galaxy Zoo and you can classify some galaxies for us. As I mentioned just now, some cosmologists might not care about individual galaxies, but will care about where they are. So this picture that is now zoomed in compared to what I showed you before, as I said, shows us the position of every galaxy in the nearby universe to us. And so we're here in the center. It's not because we're in the center of the observations. It's just that we're, it's not that we're in the center of the universe, it's that we're at the center of the observations. So we're looking out into the universe and measuring where those galaxies are compared to us. And so every point on here is a galaxy. And what you see is that the structure isn't random. The structure isn't uniform. Instead, there's areas where there's lots of galaxies, where they're all clumped together, and there's these black areas, which we call voids, where there's no galaxies at all. And so this tells us about how the universe has changed over time. We can rewind the clock back and see if our theories about the universe make the universe look the way it is today. Doing that using simulations, this is just an enlarged version of the kind of simulation I showed in that movie, where we've put particles into a box in a computer, given it some physics, given it some gravity, and hit go, and seen what happens as we fast forward through time. And so what you see again is that there's areas where there's stuff that's come together, all these yellow areas where galaxies have formed, where it's the densest, and then these kind of spider web-like structures connecting it all together. So comparing that with our observations tells us whether our theories of the universe are correct or not. We can look back through time towards the early universe. This is the cosmic microwave background radiation, the oldest light we can see in the universe. And I'm not going to talk about this much because I'm going to talk about this later on. But we can again look at how the universe was billions of years ago and compare that to our observations today and see if our theories about how it would go from an early universe to the current universe are correct. Some of my colleagues study supernova explosions. That's what this light is here. It looks like a very bright star, but this is actually the light given off when a star much more massive than the sun explodes at the end of its life. And so this star has gone supernovae, and what we can do with supernovae is use them to measure distances. We know how bright they should be, and so depending on how bright we observe them, we know how far away they are. Observations of supernovae actually led us to something called dark energy, which I'll talk about at the end of the lecture. But this is basically the idea that the universe is not just expanding, but that expansion is accelerating. Everything in the universe is getting away from everything else faster and faster. And that shouldn't be happening if the universe is just made up of what we can see. We look back through the entire history of the universe. So that's what this graphic shows us. From the present day here, where dark energy is starting to accelerate the expansion of the universe, back through time to when galaxies developed, to when the first stars were being created, to this cosmic microwave background radiation, and even as far back as this period of inflation, of very rapid expansion, fractions of a second after the Big Bang. And so mostly what I've talked about so far are observations and simulations, but a lot of what we do at the ICG as well is very theoretical work. And that's demonstrated by this photo. This is a photo of one of the whiteboards in our tea room. Don't ask me what any of these equations mean because I don't know. I could just about tell you that there's a quarter there. Something's being squared there. But I don't understand what this means. That's okay. I am very much an observational astrophysicist. But this is some of my colleagues do this work all the time. One of the PhD students who's recently graduated spent 3 years writing equations in a notebook. He hardly used a computer, and he was trying to solve equations to explain the universe. The Institute of Cosmology and Gravitation actually started as an offshoot of the maths department at the University of Portsmouth. And so we still have many colleagues who are very mathematical in their thinking, very theoretical in their application of the universe, doing things like coming up with modified theories of gravity to see whether Einstein was wrong and needs modifying for his theories of gravity to work on the biggest scales. But today I want to talk to you about the invisible universe. And before we get onto the invisible universe, I thought we should start with the visible universe. So what can we see in the universe? Well, if we go out at night and look up, we see this. We see stars. Not that often from the UK because most of the time it's cloudy. Particularly in Manchester, it seemed like it rained all the time. But on a clear night, if you go out and you look up at the sky, this is what you'll see. You'll see some stars. And this shows a pattern of stars that's very familiar to me. This is a constellation that we call Orion. And so you see immediately the 3 stars in his belt there. And then these 2 stars up here are his shoulders. And these ones down here are his feet. And I actually saw Orion as I was boarding my plane yesterday in Ahmedabad. So you can definitely see Orion at this time of the year in India. So look out for him. But this photograph was taken from a city. This photograph was actually taken by one of my friends, Stuart, in Cardiff. And so while you can see some stars, you can't see a lot of stars because of light pollution. That's what this orange haze is down here at the bottom, is all the lights from the buildings, from the street lights, from our car lights, all those lights that humans are making. What that does is it lights up the sky and it stops us from seeing the fainter stars. So to see those fainter stars, what we need to do is go somewhere dark. And then we see something like this. So hopefully you can see that there is a lot more stars in this picture. It actually shows the same part of the sky that we were looking at before, but it might take you a moment to pick out Orion. He's over here. So there's 1, 2, 3 stars making up his belt there. There's Betelgeuse, one of his shoulders, and his other one there. There's Rigel, one of his feet, and his other feet down there, foot down there. And going somewhere dark can be a bit disorientating. It can be a bit confusing if you go somewhere really dark and you look up at the stars because there's just so many that you see, and it takes you a moment to pick out those familiar patterns that you might be used to seeing from your town or your city. And so in a way, this picture shows us the invisible universe with a stray meteor going across there. That's what that is. In a way, this is the invisible universe. This is the universe that we can't see from our towns and our cities because of our light pollution. But I think that would be me not being very fair to the universe if all I did was come here and say I'm going to talk about the invisible universe and just talk about light pollution. So we're going to go beyond that. That isn't the end. So for as long as people have been people, I think we've been astronomers. I've never verified this, but I think astronomy is probably the oldest science. Because I think as long as humans have been aware, we've looked up at the sky at night. We've looked up at the stars, we've looked up at things like the moon, shown down here. We've looked up at the planets. This is Jupiter and Venus up in the sky. And we've tried to work out what's going on up there. Early astronomers will have watched the sky night after night, seen how the moon changes its phase, see how the shape of the moon changes as you go through the month, seen how the stars' positions change throughout the course of the night, see how the planets jump where they are compared to the stars night after night. And try to piece together why this is. What is the science behind this? What is driving that? And for thousands of years, all we could do was use our eyes. We looked up with our own eyes. That changed in 1609. This person here is Galileo, a famous physicist and astronomer from Italy, who is credited as the first person to use a telescope to look into space. And so in 1609, what scientists did was they took lenses, these theories of optics that had actually been known about for a very long time. But what they did was they combined lenses in a tube, these are two of his telescopes here, and they pointed them up at the sky. And Galileo looked at the moon and Jupiter, and I say he's the first person, he's credited as being the first person to do this, because actually an English astronomer called Thomas Harriot did it first. So a few months, I believe, before Galileo used a telescope to look at the moon, Thomas Harriot did it. But what he didn't do was tell the rest of the world about it. So he made his drawings, and he did not publish them. So if there are any scientists in the room, particularly any scientists in training, any students, this is a lesson to you to make sure that you publish your work, because otherwise history will forever remember someone else as the person who did that work first. And so Galileo looked up at the moon and at Jupiter. And this drawing, this page up here on the top is a scan from one of his books, showing what he saw when he looked up at Jupiter. And what he saw was a disk that was the planet Jupiter. That's what this photograph is showing here. This obviously isn't a photograph taken by Galileo, but this is similar to what he would have seen. He would have seen this big disk of light that's Jupiter. And then he saw what looked like stars, these asterisks on either side. And that's what these small dots are here. What he noticed when he repeated his observations, he looked at Jupiter over a series of nights, night after night, he noticed that the position of those stars changed compared to Jupiter. And you can see that in his drawings. On the top one, there's one here on the left, and then two here on the right. And on the bottom one, there's two on the left and two on the right. So another one has appeared during his second observations. And the distance between them has changed. So you can see there's a bigger gap between these two compared to between these two. And so what Galileo realized is that these aren't stars. What these are moons. These are moons going around Jupiter. And this changed everything, because at the time, a lot of people still thought that the Earth was the center of the universe, that everything revolved around the Earth. But if there are moons going around Jupiter, that means there's something out there that doesn't orbit, that doesn't revolve around the Earth. And so this tied in with the theories of people like Copernicus around the same time, who were saying that actually the Earth isn't the center of the universe. And of course today, our understanding has gone further, say that the Earth goes around the sun, but even the sun isn't the center of the universe. The sun is one of many stars in our galaxy, the Milky Way, and that there actually isn't a center to the universe at all. Since then, we've built better telescopes. These are some photos taken by amateur astronomers, so using telescopes that you can go out and buy yourself. They might be very expensive once you get to this picture. This picture is very good. But what you start to see is some color on Jupiter. You start to see some bands. These are the cloud bands on Jupiter. And you start to see an incredible amount of detail. Probably thousands of pounds for the telescope that did that, and a lot of work to make an image that good. And then you can get professional telescopes, the ones that we use as professional astronomers and astrophysicists, like the Hubble Space Telescope, one of our best telescopes that we have. And they show us incredible amounts of detail, not just on Jupiter, but even on the moons. There's one peeking out there that we can start to see detail on. And telescopes have allowed us to do amazing things. Telescopes allowed us to find new planets. So this is the planet Uranus, or Uranus on this side. This is Neptune on the right. Both of these planets are too far away from us to see with our eyes. They're too faint. So we needed telescopes in order to discover them. Telescopes have allowed us to see that objects we can see with our eyes are actually very different to what we might think. So if we go back to Orion and we find his belt, hanging down from his belt is his sword. And if you've got good eyes, you might be able to see that one of the stars in his belt looks a little bit odd. It looks a little bit fuzzy. And you can see this with your eyes. It doesn't even have to be from that darker sight. You'll notice there's something a little bit odd about that. And that's because it's not actually a star at all. If we use our telescope to zoom in on this, we see it's something called a nebula. It's a cloud of gas and dust where new stars are being born. And I'll come back to the Orion Nebula a little bit later. If you go to the right part of the sky, if you look in the right part of the sky at the right time of year, out of the corner of your eye you might see a faint smudge of light, which is this thing down here. I'm not even going to bother telling you how to find it because it's really hard to find. So if you want to know how to find it, its name is M31, and you can go online and find guides to how to see this. But it will be really hard to see. You'll have to be somewhere really dark, and it will just look like a faint smudge of light, and it won't look very impressive. But what that smudge of light actually is another galaxy. So a galaxy you can think of as a star city. It's a collection of 100,000 million stars, all held together by gravity. And our galaxy is called the Milky Way. Every star that we see in the sky is part of that Milky Way galaxy, but that faint smudge of light is outside of our galaxy and is an entire other galaxy out there. This is what we think the Milky Way will look like as well. So this galaxy that was that faint smudge of light contains 100,000 million stars. And telescopes have given us beautiful, stunning images of things like columns of dust and gas where stars are being born, of car crashes of two galaxies merging together. Beautiful, weird-looking galaxies that look kind of like one galaxy inside another one. And gorgeous, face-on spiral galaxies. This is what we think the Milky Way would look like. And I think that astronomy, astrophysics, cosmology, whatever you want to call the science that I do, I think it's fascinating because it's simultaneously one of the most accessible and inaccessible sciences at the same time. It's hugely accessible because anyone can do astronomy. You all can go out and look up at the sky the next time you're out on a clear night. You can observe the stars, you can look if there are any planets, you can see the moon if it's the right time of the month, and you can do what those ancient astronomers did. You can watch the sky through the night, night after night. You can build up a picture of what's happening there in the universe, and you can use your knowledge of science to try to understand it. Even if you have no vision, there are now ways that you can still do astronomy, even if you're blind. So it's hugely accessible, but it's also hugely inaccessible because I can't go there. I can't go to this galaxy and take a photograph of it close up. I can't go and grab a handful of that galaxy and bring it back to Earth and put it in a laboratory and poke it and see what it's made of. I can't go stick a thermometer in the sun to go and see how hot it is. Nearly everything we know about in the universe, we know because we can see it. Humans have only been to the moon. That's as far as humans have been in our exploration of space. We've sent satellites and spacecraft to the other planets, even out as far as the dwarf planet Pluto. But we've never been to any other stars. We've never been to any other galaxies. We know about all of this because we can see it, because we can capture the light coming from these objects in space. And so that means we have to go beyond just taking these photographs, and we have to manipulate light in different ways. And so one of the things we do is we take advantage of this. So many of you will be familiar with this kind of image from science lessons, that when you take a white light, you shine it through a glass prism here, you get a rainbow out the other side. And this is because white light is actually made of a mix of all the different colors of the rainbow. And so we call this the white light spectrum. When we take a light and we split it up into its components, we call it a spectrum. And that's what you would see if you took a white light and you shone it through a prism. But not all lights are like that. If we get certain gases and we make those gases glow, if we then shine that light through a prism, instead of seeing all the colors of the rainbow, we would only see a few. So I've got a lamp in Portsmouth. Unfortunately, I couldn't bring it with me here today. I don't think customs would have let me bring it through. But we've got these different lamps. And if I switch one of them on, it glows pinky purple. And when we shine that light through a prism, this is what we see. We see one line that's red, one line that's turquoise, and then two lines that are purple. And that's because of the gas that's inside that lamp. That lamp is made up of hydrogen gas, the most abundant element in the universe, the first element in the periodic table. And because of the way that the hydrogen atom is structured, it gives off these colors when it glows. And they mix together and they make this pinky purple color. And in fact, every atom, every element in the periodic table has a different spectrum. And so this shows you what you would see at the top for hydrogen, then helium, this one here, sodium, oxygen, and neon. And some of you may have seen neon lights before, neon signs that glow red, really vibrant. That's because there's neon gas in that lamp, and if you shone that light through a prism, this is actually what you would see. And what you notice here is that each one of these is different. The spectrum of an element is unique to that element. It's like its fingerprint. Just like your fingerprint is unique and can identify you, the spectrum is unique to the element, and so we can identify what element we're looking at by looking at what pattern of lines we see. And obviously this is great for astronomers because this now means that we can identify what gases, what elements are in our stars and in our galaxies. Because if we take light from the sun and we shine it through a prism and we see this top pattern, we know that the sun is made of hydrogen, because only hydrogen can give us those specific colors in that pattern. If we see this one, we know it's made of helium, and so on. And actually when we look at the sun's light, we see a combination of the top two, so we know that it's made of hydrogen and helium. And helium was in fact first discovered in the sun before it was discovered here on Earth. It's one of, I think, 2 things to be discovered in space before it was discovered on Earth. Don't ask me what the second one is because I can't remember, but I'm sure there's a second one. And so this technique is called spectroscopy, taking the spectrum and analyzing it. And I would say this is the most powerful tool that an astrophysicist has. It lets us identify the elements in our stars and galaxies. It lets us see what things are made of. And it also can give us much more information about how things are moving when we look at the spectrum, and I'm going to talk about that a little bit later on. One of the pioneers of this field was this woman called Lady Margaret Huggins. She was married to a man called William, and the two of them were astronomers. They lived in London, and their house was an observatory. So their house had a telescope on the roof. It sounds amazing. And they devoted their lives to astronomy. So night after night, they took their observations, and they used this new technique at the time of photography. This was when photographs were a new thing. And they were able to photograph spectra. So they were working in the late 19th century, early 20th century. So they had their telescope, they pointed their telescope at the sky, they took the light from the other end and essentially shone it through a prism to split it up into the spectrum, and then they focused that light onto a photographic plate, something that was new. And that meant that for the first time they could take the spectra of fainter stars. Before that they could only do the spectra of really bright stars, and then they drew what they saw. But by doing photography, what they could do is they could take the spectra of fainter stars. And so that's what's shown here. This is one of their photographs from a publication in 1877. This is the spectrum of the sun, and this is the spectrum of a star called Alpha Lyrae. And so what they did was they took the spectra, they looked at what lines they saw, and they compared that to what lines you would see if you made gases glow in a laboratory here on Earth. And so they worked out what these stars were made of. And one of the main contributions they made to the field of astrophysics, I mean, this was kind of the start of astrophysics. Before that, it was mostly astronomy. It was taking measurements and not really analysing it in that way. Their contribution to the field of astrophysics was to produce a book of the spectra of stars. So they took all their photographs like these, of all the brighter stars, and they put them all in a book. And they sent those books around the world so that other astronomers, when they took their observations, could compare their observations to the ones in the books and see what stars look similar and which ones look different. Today, of course, we don't do spectroscopy in quite the same way. We don't take photographs in the way that Margaret and William did. We use huge telescopes like this. This is the Sloan Telescope. It's on top of a mountain in New Mexico. It's one of the main observatories that we use in our research in Portsmouth. And what it's done is it takes observations of the sky night after night, just going across the sky, taking photographs of lots of different objects. It's taken photographs of millions of galaxies, and it's taken the spectra of over 3 million objects. So we've gone from Margaret and William taking photographs of a handful of stars to now 3 million objects just with this one telescope. And what we do is we turn the spectra into graphs. So that's what these three things are showing here. What we've basically done is taken the colour and put it along the x-axis and said how bright that colour is on the y-axis. So this one here at the top, which has got just lots of spikes, is the kind of thing that you would see if you turn the spectra I was showing you of the different elements into a graph. And so every time you had a bright line of colour, you would have a spike up here. This one looks slightly different. Instead of having spikes, it has dips, and that's because the gas in the outer parts of a star is actually taking in the colours of light. So it's taking those colours of light away from the light that you see, something that's called an absorption spectrum. And then this bottom one here is a bit like the top, but can you see that the lines, instead of being straight up, are more like that? They've been stretched out at the bottom. And that's because the gas that's giving off these emission lines is actually moving, and so that's spreading it out. And so we can understand about the movement of that gas from there. So in a way, that's the invisible universe. That's taking light that we can see. If we have a neon light, we can see the red light of the neon sign. But we can't see the spectrum without a spectroscope, without a prism. And so in a way, that's the invisible universe. But again, that's still not quite getting to the whole story, because light extends far beyond that rainbow of light that we see. There's light that goes beyond the violet part of the rainbow here, that we call ultraviolet, that you can think of as light that's more violet than violet. It's just that our eyes can't see it. And there's light that goes beyond the red part of the spectrum, that's more red than red, and we can't see it, but we call it infrared. And while we can't see these different types of light, this is truly the invisible universe now. We can build cameras, and we can build telescopes to observe this. So let's start just by showing you a nice example of infrared. This is the visible, or the optical, image of a nebula called the Carina Nebula. So this is a cloud of dust and gas here, where a new star is being formed in the center. And it's a beautiful picture, right? This is the kind of picture that you print out to stick on your wall, or you use it as your computer background. It's absolutely stunning. But as scientists, what we want to do is we want to go beyond that. We want to understand what's going on inside this cloud of gas and dust. We want to be able to see the star being formed. And so we go to infrared, and I'll show you what we see if we now take a photograph of the same part of the sky, but using an infrared telescope instead. So if you've got good eyes and you're nearer to the front, you can probably still see kind of the ghostly outline of the nebula here. But the first thing you'll notice is so many more stars in this picture. Let's see that again. There's so many more stars, and those are all stars in the background. These are things like brown dwarf stars. stars that are kind of failed stars. They've not quite got enough mass, got enough stuff to start the process of nuclear fusion that powers a star, and so they're not very hot, so they give off a lot of infrared light. And then here, up here, we see where the star is forming, and we see these two lines, what we call jets of material, coming out from that newly forming star. And so this now really is the invisible universe. This is helping us to understand stars and galaxies and the universe around us using light that we can't see. And light goes beyond just infrared and ultraviolet. There's this entire spectrum, what we call the electromagnetic spectrum of light. If you go up from infrared, you get to microwaves and radio waves. If you go the other way from ultraviolet, you get to X-rays and gamma rays. And hopefully, most, if not all of you, are familiar with these terms, even if you've never thought about them as different types of light. Because we use radio waves for communication. Your mobile phone will use radio waves. We have dishes on the sides of our houses if we want to pick up satellite TV from the radio waves being beamed down from a satellite. Microwaves are used in microwave ovens. The microwaves actually give energy to the water molecules in your food to heat it up. Infrared that we just saw is actually used in night vision. So as humans, we're giving off infrared light. If I had an infrared camera in here right now, and again, I couldn't bring my infrared camera with me because I think customs would have said something about that, and the university probably wouldn't have wanted me taking it out of the country. But if I could have brought my infrared camera and looked at all of you right now, you would be glowing because we're all giving off infrared light. Even if I turned all the lights off in here, with the infrared camera, I would still be able to see all of you. Ultraviolet, you might know as UV, the harmful rays that come from the sun. The reason that some people in the UK go and lie in a tanning bed and get blasted by UV rays to get a tan. I wouldn't recommend that to anyone. Of course it's safe, but it just doesn't seem like a good idea. We use X-rays in medical imaging, so if you've ever broken a bone, you might have had an X-ray to see where the break was. And I can never think of a everyday example of gamma rays, but if you're familiar with the Marvel universe, the Hulk becomes the Hulk in the Marvel comics and in the Marvel movies because Bruce Banner gets exposed to a lot of gamma rays. Now this would not happen in real life. If you got blasted by a lot of gamma rays, you'd probably just die. So please don't try that to become a superhero, but that's the story, and that's probably where most people have heard the term gamma ray before. Gamma rays are used to irradiate cancerous tumours. There's something I didn't know. Thank you. And so those are all examples of the electromagnetic spectrum, but those are everyday examples, and I'm here to tell you about the universe, not about comic books, although I'd be happy to talk about comic books later. And so what I thought is that we would go through the spectrum very quickly and have a look at the kinds of objects we can see at these different wavelengths. And so we'll start with radio, and I am a radio astronomer by training. I did my PhD at the Jodrell Bank Observatory, which is one of the main centres for radio astronomy in the UK, and so I'll probably talk about radio too much, but please indulge me. At radio waves, I want to show you more of these active galaxies. So these are the galaxies that I studied for my PhD. This rather unimpressive looking blob here is an elliptical galaxy called M87. This is a photograph taken by an amateur astronomer. So this is, if you get a really good telescope and you image this in your back garden, this is probably as good as you can get with M87. But we can point the Hubble Space Telescope at it to see the galaxy in much more detail. And that's what this picture shows. Now we've zoomed in so much we're only seeing a quarter of it. So that's the center. We're kind of seeing this quarter of the galaxy. And you immediately notice that there's something odd about this elliptical galaxy because there's something coming out from the center. You don't see this in most elliptical galaxies. Most elliptical galaxies just look like a smooth blob of stars. But it's really when we look at the radio waves that we see how impressive this is. So this is now the radio image. It's just rotated round, so this is the center, and that thing coming out there is the same as that thing coming out there. And so there's something coming out from the center of this galaxy. And what we call this is a jet. So this is a false color picture. picture, where it's red is where there's a highest intensity of radio waves, and then it goes to yellow and then blue, then green and then blue, because obviously we can't see radio waves with our eyes, we have to give them colors to see them and to interpret them. And so this jet is coming out from the center, and this jet is made up of charged particles, like electrons, the negative part of the atom, and they're spiraling round a magnetic field. And when electrons do that, they give off radio waves in something called synchrotron radiation. And in fact, in M87, there's two of these jets. We can only see one of them, but you have to imagine that instead of this one going just off this way, it's actually more like it's coming out at an angle like that, like my arm is. And so there's also a jet going in the opposite direction, going kind of into the board and behind the screen. We don't see that one going behind, but what we do see is on this side, all this wiffly stuff, and that is the term that radio astronomers use. They call it wiffly. All this wiffly stuff is when that jet is ploughing into the material outside of the galaxy. And so this image was taken with the Very Large Array. That's what this is. That photo I showed you at the start of me standing inside a radio telescope is me standing inside one of these dishes. When you go to a radio observatory, a lot of the time you go inside the dish, apart from the GMRT, because the GMRT ones are made up of mesh, so that's not a good idea. They're not a solid structure. What you'll notice here is that it looks like there's lots of radio telescopes in this picture, right? There's one there, one there. There's a whole load of these dishes, and they're all pointing at the same part of the sky. And that's because we want to get really good resolution in these pictures. We want to get a lot of detail. So you'll probably be familiar with the term resolution with your camera phone. You want to have the highest number of megapixels in your photographs coming from your phone camera to get the most detail in your pictures, the highest resolution. And so we want to do the same thing with our radio telescopes. But the thing is that the resolution, we can't just build the same size telescope for every type of light and get the same resolution. The resolution depends on the type of light we're looking at. And for radio waves, we need really big telescopes. So the Hubble Space Telescope is probably the best optical telescope we have. It gives us really high resolution images of the universe. To have a radio telescope with the same resolution as the Hubble Space Telescope, which is 2 meters across, to have the same resolution in radio, we'd need a telescope the size of England. And for some reason, people in England like their houses and don't want us to just take out the entire of like Birmingham and all the Midlands to build a giant radio telescope. So what we do instead is we build these smaller dishes, we point them all up at the same part of the sky, and we connect together the signals that come from those telescopes. And it's as if we had a telescope that was the size of the area that all those telescopes cover. And so that's the VLA, and as I said earlier, you have the GMRT here in India, which does a very similar thing, looking at very low frequencies. So that's radio. Microwave, to astronomers, microwave and radio are very similar, but I thought I would pick something out to show you, and that's the entire sky. So this photograph here shows the Milky Way Galaxy. This is us looking kind of through the center of our Milky Way Galaxy here. The Milky Way Galaxy is flat. It's a bit like 2 fried eggs stuck back to back. You imagine making 2 fried eggs sunny side up, stick them back to back, you'd have a ball of yolk in the middle, and then there's disk surrounding it. And that's what we think a spiral galaxy looks like, and that's what we think the Milky Way looks like. This is us essentially looking through that disk of white there. And so that's the entire sky at optical wavelengths, at visible wavelengths. This is the entire sky in microwaves. So again, this is a false color picture where the highest intensity, the brightest microwaves is the white, and then the blue, and then there's these speckles of yellow and pink there. And what we see is a lot of microwaves in this line across again. That's all the microwaves coming from the Milky Way, but in this picture I don't actually care about that. So astrophysicists had to spend a long time getting rid of all of that emission from the Milky Way, basically rubbing out the Milky Way from this picture. So what some of my friends were doing for their PhDs and postdocs in Manchester. And then you end up with a picture like this. So I showed this briefly at the start. This is the cosmic microwave background radiation. This is the oldest light we can see in the universe. So our theories of the universe say that the universe began with the Big Bang 13.8 billion years ago. This is light that was emitted 400,000 years after that. So for more than 13 billion years, this is light that has been traveling out across the universe. And we pick it up today as microwaves. Now what we can do, and this is a little bit weird, is that we can say that this light has a temperature. So we can say that this light is very cold. Its average temperature is about 3 degrees above absolute zero, so it's really, really cold. And it looks quite similar in all directions, but there are these tiny, tiny changes in the temperature, and that's what these colours, these speckles of red and blue show. The areas that are red are parts of the sky that are maybe 1/1,000,000th of a degree hotter than that 3 degrees above absolute zero. And the blue areas are where it's 1/1,000,000th of a degree colder. So these tiny, tiny changes, tiny, tiny differences in the temperature of this radiation. And in fact, we think that all of the structure we see in the universe today, all the galaxies and all that large-scale structure I showed you at the start, actually comes from these tiny changes, these tiny differences in the temperature. That one was taken with this telescope, the Planck satellite. This is an artist's impression, a drawing of it, because Planck actually got sent off to a point in space that's 4 times further away from us than the moon. So we can't take a photo of that. There's no people there to take a photo. So this is an artist's impression of the telescope. Infrared we kind of saw already, but I'll show you another example, and we'll go back to our Orion Nebula. So remember that faint fuzzy knot star in the belt? This is what it looks like if you have a very good amateur telescope. And if you zoom right in, this is what you see with the Hubble Space Telescope. So again, it looks really beautiful, but it looks dominated by all this dust and gas. There's 4 bright stars here in this cluster, but you can't see many stars. And then this is the infrared image. And in fact, in this picture, there's more than 300 young stars and brown dwarf stars, those pale stars that I talked about earlier. And so you can see, just like we saw in that example before, that the infrared lets us see through that dust and lets us see these other stars behind the nebula. Both those photographs were taken with this telescope. Now, this is a real photograph of this telescope. This is the Hubble Space Telescope. The Hubble Space Telescope is in what's called a low Earth orbit, and that means that when NASA was still flying the space shuttles, which are now retired, the space shuttles could go to the Hubble Space Telescope, which is a good thing because it needed fixing. Well, it got fixed after it was launched, and then it got upgraded a few times. So I think there were 4 servicing missions to the Hubble Space Telescope in total. We'll skip out visible because we know about visible, we've seen that. We go to ultraviolet, and for ultraviolet I want to go back to the Andromeda Galaxy, or M31. And so that's this faint smudge of light here. This is the picture from the Sloan Telescope, and I showed you earlier, showing you that it's a spiral galaxy. Remember, our fried egg stuck back to back. There's our ball of yolk in the middle, and these are the whites, the flat disc surrounding it with these spiral arms inside. And so what you notice here is that the center looks kind of yellow, and the spiral arms look kind of blue. And that's because the stars in the center of the galaxy are older, and they're not as hot. They're still really hot. They're still like thousands of degrees hot. But in astronomy terms, they're not as hot as the other stars. So they're cooler, and they glow yellow and red. And in the arms is where new stars are being formed, and when stars are formed, they're really hot. We're talking tens of thousands of degrees, sorry. And so they glow blue. When we look at this in ultraviolet, 2 things you notice immediately. You hardly see the center, but what you do see is this ring, this really obvious ring in the spiral arms around it. And this ring is where those new stars are being born. So all those nebulae that we've seen, where stars are being born, those are all in the arms, the spiral arms of the galaxy. And so that's where all these new stars are being born, and when they're born, they glow so hot that they give off ultraviolet. But I think it's still a bit of a mystery why there's such a prominent ring surrounding this galaxy. And you can hardly see the center because those stars are so cool that they don't really give off many ultraviolet rays at all. Now this photo was actually taken using images from this satellite. This is the Swift satellite, again an artist's impression, a drawing. It's an X-ray telescope, but it also had an ultraviolet camera on it. And this picture, I think, is really nice because a summer student did it. A summer student working for NASA over one summer piece together that photograph from these observations. At X-ray, I want to show you something that's kind of weird. Doesn't look great there. This is the Crab Nebula. Just kind of looks like a cloud, doesn't it? Doesn't look that impressive. The Hubble picture is much better. Wow. This is something that we call a supernova remnant. So this is what you get when a massive star, much bigger, much more massive than the sun, explodes at the end of its life. We spoke about that a little bit earlier. I said that we can use these supernovae to measure distances, but we can also study the supernova itself. And so what this picture is showing you is all the gas in the outer parts of the star that's been flung out by the explosion. But what happens in the center of the star is at the core of the star, the center of the star, collapses. It shrinks, and as it shrinks, it gets compacted, it gets denser and denser until you're either left with something called a neutron star, which is a star made up just of the neutral part of the atom, the neutrons, or you get a black hole. And in the case of the Crab Nebula, what's left in the center is a neutron star, and that neutron star is spinning. And so it becomes something that we call a pulsar, because it gives off as it spins, it gives off two beams of radio waves and X-rays. So if you can imagine a lighthouse with two beams of light coming out, and it goes round, and these beams of light sweep past you. I'm going to stop before I get dizzy. Every time it sweeps past you, you see light, right? So with these pulsars, every time the beam sweeps past us, we see a blip of radio waves or X-rays or both. And so in the case of the Crab Nebula, we see it in X-rays, but not only that, we've actually managed to take an image. And again, I keep on saying we. I'm using we as all astronomers. I haven't done this. But some astronomers took an image, built up an image of X-rays coming from this. And you can see this pulse coming out and this material swirling round the neutron star in the center. And that was taken with the Chandra X-ray telescope. Again, a drawing of it. We have to put our X-ray telescopes in space because the atmosphere stops X-rays from coming through, which is a good thing because X-rays are harmful to us in too high a dose. And so we wouldn't be very happy if we were being blasted by X-rays from space. And then finally, gamma rays. Gamma ray astronomy is a much newer area of astronomy because it's really hard to take observations at gamma ray. So all of those telescopes that I've talked about so far work in pretty much the same way. They work with mirrors. So you have a curved mirror. Your radio waves, for example, in our dishes, hit the dish and get focused up to a point. And we can do that with all these different types of light, but gamma rays are just so energetic that you can never bounce them off at a big enough angle in order to focus them. And so gamma ray astronomy is much newer than the other types of astronomy. We have to do something a little bit different. So all I can show you at gamma ray is the entire sky again. And this is the sky in gamma rays. So here, yellow is the most intense, and then red, and then blue, and then finally black. And again, we notice lots of gamma rays coming from the Milky Way. That's what all this is. It's not that the Milky Way gives off a lot of gamma rays for a galaxy, it's just that we're inside it, so it's easier to pick up those gamma rays coming from the Milky Way. What I'm really interested in is all of these little blobs below and above. Because if those blobs are outside of the Milky Way, if they're outside of our own galaxy, the majority of them will be active galaxies, will be the same galaxies that we see really brightly in the radio waves. And so we think that the gamma rays are also coming from those jets that I showed you with M87. And what I was doing for my PhD was trying to look at the physics behind the process that makes them give off so many radio waves and also so many gamma rays at the other end of the spectrum. This is the Fermi Space Telescope. This is the telescope drawing of the telescope that took those observations. It works slightly differently to the other telescopes, as I said. It works more like a detector in a particle accelerator. And so what happens is the gamma ray hits the telescope and it can change into a pair of particles. And those particles kind of shower down. They can change to other particles and cascade down until they hit a detector further into the telescope. And then you can measure the energy of those particles. You can measure the direction that that cascade came in, that shower came in, and work out what object in the sky it was from. So that's our entire spectrum. a reminder that you can see the same object in all the different wavelengths. What I showed you is different objects, but we can use all these different telescopes to look at the same thing. So this is the Andromeda Galaxy again here, but shown in radio waves, microwaves, infrared, optical or visible, ultraviolet and X-ray. And you can see it looks very different in all these different wavelengths, and it's showing you different physics, different parts of the galaxy, different processes going on inside it. Now, everything I've talked about so far, all these stars and all these galaxies and all these planets, all this stuff that we see with our telescopes, that's all what we call ordinary matter. That's all stuff made up of atoms like you and me. But actually, that only makes up about 5% of the universe. And the rest of the universe is made up of dark matter and dark energy. So I want to very quickly try to explain those before I finish. And so one of the first pieces of evidence that there's other stuff in the universe that's not ordinary matter, this stuff we call dark matter, came from looking at galaxies like Andromeda and looking at how they rotate. So these galaxies are spinning round. So you can imagine the left-hand side is coming towards you and the right-hand side is coming away from you, and it's going round like that. We know this because we observe the spectrum coming from the different parts of the galaxy, and it doesn't look the same everywhere. So if this rainbow with bits missing, because it's an absorption one, is the spectrum that we would observe if it's not moving, on the side that's moving away from us, we see all of these lines have moved slightly to the red part of the rainbow. Can you see that? It shifted slightly up this side. And on the other side, on the left-hand side, where it's moving towards us, all those lines have moved towards the blue part of the spectrum because of the motion. And so what we can do is we can measure the speed of the different parts of the galaxy. And then we can say, okay, we understand physics, we understand how things move, how things rotate. We can work out how fast it should be moving as we go from the center of the galaxy out. And so in the center of the galaxy, it's basically like a solid ball. And so we think it should move like a wheel. So the speed should increase as we get further away from the center. And then out in the disk, we think that it should all move basically like the planets in our solar system. So the speed would drop off with distance. And so we build up what we call a rotation curve, where this is how far away you are from the center's here, and this is getting further away. This is your speed or velocity. We say in the center where it's solid, the velocity increases as we go further away, and then it should drop off like the planets do. But that's not what we see. What we actually see is that the velocity in the outer parts of the galaxy stays constant. What this tells us is that there must be more stuff in the outer parts of the galaxy, all out here, that has a gravitational effect that is keeping all those stars and gas moving at that high speed, but we don't see it. It doesn't interact with light in any way, and so we call it dark matter. And one of the pioneers of this was this woman, Vera Rubin, who sadly passed away recently. She did this work looking at the rotation of galaxies, the movement of galaxies, and noticed this odd thing happening. But she wasn't taken seriously at first. People encouraged her to study other topics, to leave behind that research that didn't make sense. But she persevered with it, and now it's recognized that dark matter and the rotation curve work that she did was correct. And then finally we have this stuff called dark energy, which I can't really tell you about because we don't know what it is. But basically what we see is that the universe is expanding, everything is moving away from everything else in the universe. But if the universe was only made up of matter, what you would expect is that the expansion would be slowing down because gravity would slowly be pulling everything back together. But we don't see that. What we see is that everything is moving away from everything else, and it's getting faster and faster in that expansion. So we see this accelerating expansion happening at the present day. We can't explain that, so we've invented this thing called dark energy to try to explain that. And that basically means that if you look at the energy content of the universe, you end up with 5% as ordinary matter, that's this yellow wedge here, about 27% as dark matter, the blue wedge there, and the universe is dominated at 68% by the purple, by the dark energy. And I just want to finally say that we've just recently opened up a new window on the universe. Everything I've talked about so far has been about light, even if it's invisible light that we can't see. But a few years ago, we had the first detection of gravitational waves, of these ripples in space-time from two black holes merging together. And I'm really excited about this because it's an entirely new way to observe the universe. This isn't electromagnetic radiation. This isn't us using any form of light. This is us detecting black holes merging together from the ripples in space-time. And so I'm really excited. I've been talking to people here today about the new gravitational wave detector that will be built in India, LIGO in India. And I can't wait to see what happens with this, because we have no idea what gravitational waves will show us. Just like when Herschel first detected infrared light and realized that the rainbow went beyond what we could see, he could never have imagined all those objects that I showed you today. So while we know we expected to find gravitational waves from black holes merging together, from neutron stars merging together, I think there's an entire universe of possibilities of unknown things that we could detect with gravitational waves. So I will finish there. If any of you are on Twitter, I should have said at the start, I'm Jen_Gupta on Twitter. On Instagram, I'm Jen with 2 underscores Gupta, but all you'll see is photos of my dog. You can get in touch with me on my website. This is my department's Facebook and Twitter account, and you can find out more about us there. Thank you very much.
Thank you, Jen, for this lovely lucid talk. It summarizes almost every object that astrophysicists deal with. So after this talk, I'm sure there must be a lot of curiosity in the crowd. So as Jen said, she's happy to take a few questions. If you raise your hands, we'll come to you with microphones. Could you please raise your hands if you have any questions to ask?
Yeah.
Yes, please. There, front.
Thank you so much for such a great presentation.
Thank you.
I looked at the picture which was from microwave for the universe, and it was like kind of an egg-shaped.
Yeah.
Was it? I mean, is it like it is really egg-shaped, and beyond that everything is just dark matter and dark energy?
Okay, so I should have explained this picture better. So this is, and all these pictures are pictures of the entire sky. But what we've had to do is turn them into flat pictures. So if you've ever seen a globe of the Earth is a ball shape, and you have globes of the Earth, what we do is we kind of unfold that to make a 2-dimensional flat map of the world. So these all sky images are basically the same as that. If you can imagine going to every point on the Earth and taking a photo directly up and stitching it all together, what you would end up with is photographs of a sphere of a ball surrounding the Earth. And so just like you can take the globe of the Earth and unfold it to a map, you can take that globe of the entire sky and unfold it to make a 2-dimensional picture of the sky. So this is everything contained within this this ellipse. There's nothing outside of it. It's just taking our sky and putting it into a way that I can put it up into a screen. Does that make sense?
Yeah. Thank you.
Okay.
Lovely. Nice
Yeah, we
question.
have
Can we move to another question? Yes, one in front, and then we'll go to the question back.
Similarly, at the start of your presentation, you talked about the structure of the universe, and there was a similar map. So can you just elaborate how that is to be read?
Yeah. So where's the best picture? So this is just showing some of it. So it's actually a square picture, but I've cut it off because of PowerPoint. So this is the center of the picture, and this is the large-scale structure. That essentially what we've done is, and again I say we, this is what scientists, my colleagues have done in the Sloan Digital Sky Survey collaboration, observed galaxies and measured their positions compared to us. So measured how far away they are, and basically plotted them on this picture and kind of taken the 3D and squashed it down. And then the reason there's this wedge, the reason there's nothing in these sides is, I think, because our Milky Way is in the way. So because we're in the Milky Way Galaxy, if you look in certain directions, you can't see through the Milky Way in the optical. And so we can't observe these parts. Probably also the Earth is in the way, because from New Mexico you can only see certain parts. You can't see all the southern parts of the sky, so you can't see that part of the universe.
So this is like a cross section with the right ascension plotted?
Yes, so it's right ascension going around. I think, yeah. So there's 3D representations. 3D
It's also
representations
distance
of
from
them.
us. So from the center outwards, it's the
Yeah.
distance to the galaxy.
Yeah.
Every point that you see farther off is farther from us, while
this
the
is-
points closer are close.
Yeah, so what's being cut off here is the redshift going out, so the distance going out.
Yeah, please. Sonal, can you come here? Sonal, can.
How do we understand that a star is young or old? Means if a star died in the Jurassic period, we would take it as we would take it as if the star died today.
Yeah, so there's kind of 2 questions in that. How do we know the age of the star, and what does it mean when we observe it today? So the age of the stars, we can do things like look at the different elements inside stars, and look at their temperatures, and look at their brightnesses. Because what we see is that stars follow a relationship between their age and their brightness and things like that. And then as a star gets older, it will run out of hydrogen to fuse together to form helium, and it will start to fuse together the heavier elements. So we can look at how much of different elements inside a star to tell how far it is through its life. The question of looking at stars and what now is a great question, because light has a speed limit. So light goes at a certain speed, which means it takes time to get to us. So even for the sun, the light that hits us from the sun left the sun 8 minutes ago. So when we observe the sun from Earth, and never look directly at the sun with your eyes because you will damage your eyesight, but if we use a special solar telescope to look at the sun, we're actually seeing it 8 minutes in the past. And all those stars that we see, we're seeing the light that left them thousands of years ago. And so, yeah, we kind of just have to talk about stars as we see them at the moment, because that's all we can do. But and even then, when we look at galaxies, we'll have seen them in the past. But you kind of don't think about that too much, because it starts to hurt my head. I don't know about you. Yep.
Dr. Gupta, if you could please talk about the idea of multiple universes. Is it really a theoretical idea, or does it have any practical implementation?
The,
And the second-
theory of multiple universes,
Yeah,
multiverses.
multiverses.
Yeah.
And one more question to follow up is, they are talking about quantum physics. So does it have any bearing or effect, or the research in quantum physics, will it open up some other part of universe that we already don't know? Thank you very much.
Okay, so the theory, thank you, the theory of multiple universes certainly is a serious scientific theory. It is being researched by professional physicists. I think the Astronomer Royal, Sir Martin Rees in the UK, is a big believer and popularizer of theories of multiple universes. I think there is no evidence yet that there are multiple universes. There are ways that you could think about looking for them. So if you can imagine universes being a little bit like soap bubbles. So if you've seen soap bubbles on the sink or something, and you have bubbles stuck together, if you imagine that if you were standing inside one of those bubbles and there was another bubble stuck on yours, what you would see is a circle where that bubble touches, where the edge of that bubble touches yours. And so people do things like look. One of the ways that it's thought that would manifest is that you would see a giant circle in the cosmic microwave background radiation. And some people did claim a few years ago that they had seen that, but it wasn't a good enough result for the majority of the community to accept it as a scientific result. That's about as much as I can say about multiple universes. It's not my area of expertise. I think it's not something that's been researched enough to say either way. And quantum physics, quantum physics definitely is not my field. That's about, yeah, I wouldn't really want to comment on something that I'm not.
So we have one question there, and
Yeah.
in the front.
The microwave, when you showed the picture, you said that's the oldest light,
Mm.
right? So would you explain that? Is the light that generated at the Big Bang, or what is that?
So the cosmic microwave background radiation is the oldest light, emitted 400,000 years after the Big Bang, and that's because before that time, the universe was opaque. It was like a fog, because the universe, all the stuff in the universe wasn't in the form of atoms. All the components of the atoms, all the bits that make up atoms, were separated. So you had your electrons, you had your neutrons, you had your protons, and they were all separated from each other. And so what that means is that every time light tried to escape out through the universe, light tried to travel in a path for a long time, it would hit an electron or hit a proton and get bounced in another direction. And then at this point, 400,000 years after the Big Bang, the universe had cooled down enough that when electrons and protons and neutrons tried to stick together to form atoms, it was cool enough that they could stay in that form. And so at that point, the universe became neutral, and that meant that and light doesn't interact with neutral atoms in that same way, so the light could then travel out across the universe. And so some of it's been traveling out ever since, and that's what we pick up as the microwave background today.
Take a question from the young person there, and then one there. So we don't have much time, sorry. Let's make these the last two questions.
Okay.
Dr. Gupta, I have two questions regarding gravitational waves. As you said, we can see a lot of amazing things through them. So why can't just we see things inside a black hole or dark matter through gravitational waves if they are just ripples in space-time?
So gravitational waves, what we observe is the effects of things like black holes. So what happens is black holes merge together and they cause space-time to ripple. And so they're not really a tool that you can use to observe the universe in the same way as light. It's kind of, I think it's really weird, and I'm still trying to understand it myself about how we can, is it correct to say that we have observed black holes by seeing these gravitational waves coming from them? Because it's not using the word observe, in air quotes, in the same way that we're used to thinking of observed as light coming from things. That's about the best answer I can give you. There are some experts in gravitational waves at this institute, probably in this audience, who might be able to answer me better on that one.
If I may add, the gravitational waves are really weak, so you can't really detect them, like all of the gravitational waves. So what we have detected are the strongest of gravitational waves, which are caused by huge collisions of black holes, etc. So the weak ones are yet to be detected. We'll need huge detectors the size of the solar system maybe to detect those. That's still a little bit ahead in the future.
Yeah. And the other thing is that we only pick up the gravitational waves that have been detected have only been the strongest signals that are emitted at that moment that the black holes finally merge together. And so the signal's over very quickly. It's kind of like it would be the equivalent of a supernova explosion, the flash of light, and then it's gone forever. There's no repetition of them.
Last question.
I did not understand the term dark matter or dark energy.
That is good because none of us understand what it is yet. So as I said, I can explain dark matter much better than dark energy. So dark matter is basically, in a number of different ways, we observe that there's much more mass, there's much more stuff in the universe than we see from light, from any kind of light that I've shown. And so I showed you the rotation curve of galaxies. If you can imagine taking a yo-yo, and taking it at the end of the string and swinging it around your head. Okay, if you let go of that, it will fly away. Yeah? So that's basically what should happen in these spiral galaxies if all of the galaxy is only the stars and the gas and the dust that we see, is that the stars in the outer part of the galaxy are going so fast that they should just fly away like your yo-yo flies away. But there is something holding those stars and gas to the galaxy, and so what we all think it is this matter that has gravity. So the gravity of the dark matter is holding all the galaxy in, but it just doesn't interact with light, so we don't see it with our telescopes. There's other ways that we've seen evidence for dark matter. Stuff that has mass actually bends space-time, so it can act like a lens. And so you can kind of weigh the universe using that. And we see in things like galaxy clusters that there's a lot more mass in them than you observe with your telescopes directly. So there's various pieces of evidence for dark matter, and I would say that the majority of astrophysicists and cosmologists think that dark matter is a physical thing, that there is some kind of particle that is having this effect that has gravity but doesn't interact with light. Dark energy, I'm less certain about. As I said, what we observe is that the universe, so the universe is expanding, and the galaxies are being carried away from all the other galaxies in the universe. And one way you can think of that is if you bake a fruit cake. So you can imagine you've got a cake mixture that's got lots of raisins in it, or lots of currants in it. And you put that cake mixture into the oven, and the entire cake rises, it expands. And the distance between all those raisins increases. So all the raisins get further away, all the fruit in the fruit cake gets further away from all the rest of the fruit. And so we think that galaxies are like the fruit in the fruit cake, and the universe is the batter. And so all the galaxies are getting further away from all the other galaxies as the universe expands. But as I said, what we see is that not only is it expanding, but it's expanding faster and faster. And so this term dark energy has been invented, which is something that is working against gravity, kind of, to push the universe accelerating out faster and faster. Now, there's two ways of thinking about this, really. One way is that dark energy is a physical thing, again, a bit like how we think dark matter is a particle, that there is actually something in the universe that is causing this. The other way to think about it is that maybe we need to modify our theory of gravity. So if you've learned about Newton and his laws of gravity, Newton sat under an apple tree, as the story goes, and an apple fell on his head, and he wondered, why does everything always fall down? And he came up with these 3 laws of gravity. And Newton's laws of gravity work really well here on Earth, but they don't work in space well enough. Gravity is the same reason why all the planets orbit around the sun, and in particular Mercury's orbit, the innermost planet. Newton's laws of gravity can't quite explain the path that it takes around the sun. And so Einstein came along and modified Newton's laws of gravity. He changed them, he updated them to explain how things move in the solar system. And so maybe what we need to do, and this is something that my colleagues are working on in Portsmouth, maybe we need to make another modification to gravity, to Einstein's theories of gravity, so that we have a theory of gravity that works on Earth, that works in the solar system, and also works on the biggest scales to explain why the universe is accelerating in expansion. Maybe there's no physical thing of dark energy, maybe it's just that we need to understand gravity better. But no idea which one it is, and I think that's really exciting because it keeps us all in jobs, and it means I think it's just really great that I can stand here and tell you that we only understand 4 or 5% of the universe, and you all sit there going, okay, that sounds reasonable. It's really exciting.
Yeah, that's lovely. I can see that there's a lot of curiosity about this invisible universe, and you can find out more about it on the National Science Day, when we'll have the practicing astronomers actually putting up posters and standing beside them trying to explain your questions in a way you will all understand. So please come for that. You'll find your answer about dark matter, dark energy, gravitational waves, cosmic microwave background, X-rays, and just remember that you're right now next door to an institute which works on all of these fields. There are some infrared cameras being made here. There's a UV telescope being made here. There are people who work on X-rays, and the gravitational wave detector in IUCAA is a lead institute. So we're quite privileged in that way to be here in Pune and be so close to IUCAA, which works in all these fields. And we are privileged that we could have Jen come here, Dr. Jen, to give us this beautiful talk, lovely visuals. Thank you again, and thank you all for coming. We'll see you again for the next talk. In case you want to know more about our activities, please either follow us on Facebook. We have a page called SciPop, short for Science Popularization, SciPop. You can follow that. Or we have an email, scipop@gmail.com. You can email us to put you on the emailing list. We'll update you about other future events for that. Thank you all for coming. Good evening. Bye.